Hi, my name is KellyBobbitt. I'm with Mike Bobbitt and Associates. We're a local GIS firm that specializes in working in vineyards. And I've been very kindly asked for GIS Day to give a presentation on how we've recently started using LiDAR data for our vineyard planning and development usage. So first thing, why are elevations important for planning a vineyard? Well, when we are on a project, we start by compiling all the data that we can for the area. Recent aerial photos, any contours that are available, creating slope maps, aspect maps or layers, bringing in NRCS soils data to give a feel for what soils might be found on the project, and also looking at USGS topos for things like drainages, blue lines, stuff like that, that might be significant in how the vineyard is developed or laid out. So one of the most important ones immediately is slopes. Because of restrictions and safety, you can't plant on every slope. And so what we see here is how we've looked at the slopes. And in this particular case, we're trying to identify areas without heavy tree coverage that are less than 30% slope. That's kind of where things start getting a little dicey as far as slopes and using tractors. And so as you can see, we've identified those areas and started giving them acreages after we've digitized the extents of them. So we can start looking at the size of the proposed project. Then the next one is aspects. Aspects is what we use to break up blocks. So there might be a block with several aspects on it or an area that needs to be broken up for safety, because what we're trying to do is get in the steeper areas, the tractors going straight up and down the slope as much as possible so that we don't have as much side slope. And, it's really a safety issue. So examples right here, if I look at this area right here, I can see that there's an aspect there, another one there, and probably a transitional aspect right there. And since this is all I knew from the last one, reasonably steep stuff, I have a feeling that that's going to get broken into 3 blocks. So when I look at the final designs, as you can see, they were broken up into 3 different blocks and different row directions for safety's sake. So that's how we use the slope and the aspect. So how did we start using LiDAR? Well, I go back 9 years ago. There was a GIS users meeting and a wonderful presentation by Russ White over at Cal Poly. And his presentation was more about open source data. But in there was also a segment on LiDAR data, recent LiDAR data that was becoming available. Fascinating technology, and it really, something stuck with it for me. His presentation, the LiDAR was focused more towards urban landscape. I think it was downtown Slow, some buildings down there. And when I went back and investigated, this is neat technology, how can I use it? I found that back then there was very little coverage just along here because of Diablo and a few other things along the coastline. Not a lot of vineyard type areas for me. So it kind of went into the back burner. And then just a couple months ago, I'm having coffee with a local GIS professional, and she mentioned that the LiDAR data coverage is much more significant nowadays. I had lost track. Through the pandemic, didn't always have GIS user meetings. I just wasn't networking. And I'd completely lost track of what was going on with the LiDAR data. So I immediately returned to the office and did a kind of a deep dive on the subject just to see, well, how significant was it? And the coverage is very significant. It is in green. The different colored greens are different accuracy of LiDAR. But pretty much most of the vineyard areas on California coast is now covered. So all except down here, kind of strange, Temecula isn't covered yet. So hopefully that'll happen soon. So in my deep dive, I started looking, doing some Google searches. Where do I get the data? And how do I get it into ArcMap and use it? That's not always as easy as you think. So a few YouTubes and Google searches later, I started coming up with a flow. So first of all, I found you download it from the national map. And so what you have to do is select your area of interest, and you can either download all these this grid of data, or whatever you want to call them, piles of data, I think would be a better term. Or you can just get a CSV files, not CVS, CSV file that lists all the different tiles that you're going to need for that area. So I found I can get a uget.exe, which was a batch download app that I could then just put this CSV file in, and it would download all that data for me. Now, these are in LAZ format, which is a highly compressed format. So I would need a way also to turn it from a LAZ to decompress it into an LAS, which is what ArcMap wanted. And so I found a LASzip.exe sitting there, and downloaded that, and could then convert in a bulk way all the tiles into LASs. So now I've got the data ready. Now I get to go to ArcMap, and I go into ArcCatalog and create a new LAS data set. From this, I then add all the LASs that used to be LAZs before I decompressed them, and bring them into that data set. Now, one important thing I recommend is check the coordinate systems. Here's why, and I don't know the reasons yet. I haven't looked at this data enough to understand all the differences. Sometimes in some places in California, when I've downloaded the data, they've been in UTM meters, and others they're in state plane and feet. So why is that important? Because the elevation of the UTM ones is in meters. So you'll need to convert those into feet at some point to get the correct elevations if you work in feet. So very important to check your coordinate system. For the data I'm using here, they were in state plane and they were feet already, so I didn't have to do any more. So once you bring this LAS data set into a project and you zoom in, you'll see all these LiDAR returns. Now, one thing I also want you to notice is they're not a systematic pattern. They're kind of random in a way. And one of the toolbars that you need to use is a LAS dataset toolbar. And the first thing you need to decide, depending on what you're trying to do, is, do I want to look at all the returns, just the ground returns, or maybe just the first returns? So very important you do that right at the beginning, depending on what you want to do with it. Once I've set that, then I can convert the LAS into a DEM. And down here, I can decide what resolution I want to make that DEM. From this, I go ahead and use Image Analyst to create hillshades, create contours, create slopes and aspects from this from the resulting DEM. So these are all the pieces that I use. So first thing is, how much is too much? It's so tempting to just create everything at the highest resolution possible. And that's what I did straight out the bat. It's like, this is so cool. I've got a new toy. Let's just, make it as useful as possible by going as high a resolution. And one thing I want to point out that I point out earlier is, these LiDAR returns are not perfectly spaced out. And in fact, they're typically, I found in this particular data set, say 1 to 3 feet apart. And you can see like this line through here, really dense, not so dense, things like that. So one of the things about ArcMap is you can create a DM of any resolution. I could make it a 1-inch DM pixels. Does that mean that it's that accurate? Maybe not. So one of the first things I did after I tried doing everything at too high resolution, realized that might not be correct for everything, is I did some comparisons of a 2-foot DM that I created, a 10-foot, 20-foot DMs to see what works best for what. And again, created my hillshades, my slope, my aspect, my contours. And here's what I came up with. For the hillshade, to me, that's just a no-brainer. Use the most maximum details that you can use. And so here is the hillshade of the ground filter. So this takes out all the trees, everything else, and just for the ground. And what was significant for me when I did this hillshade was the drainages here. I mean, we can see the drainage kind of in the aerial photo, but not as well as I can in the hillshade. So one of the things I need to do is digitize those drainages, put them in so that we aren't disturbing any water flows when we're planting the vineyard. The other thing that was amazing was how fences often jumped out too in these hillshades. That's how accurate they are. Here's another hillshade done with first return. So this does tops of trees as well. And how do I use these? Well, I already mentioned about digitizing drainages. It also shows roads quite well, fences. And one of the things for me also was tree lines. If I look at the aerial photo, there's a lot of shadowing to the north side of the trees. But on this, I don't get any shadowing. It's all disappeared. So more accurate for digitizing tree lines. Slopes. Again, comparing a 2-foot, 10-foot, and 20-foot DM. What I found with this 2-foot is it's very cool, but what it's doing is taking a slope of everything that's 2 foot by 2 foot. So it could be like this 1 second, like this another second, this. And it's just very noisy, like in this area. And what I'm in a perfect world, what I want is I want to know where, say, 30% starts and then where it ends again, very defined areas. And as you can see, once I get to a 10-foot DM, I'm starting to get less noise in there. And 20-foot DM, I think is a kind of a nice a balance of accuracy and generalization, because one thing I'm going to do later is reclassify this data into polygons, all the areas that are more than 30%, all the areas that are less than 30, and take out the vegetation, and then that's going to be my areas of interest. So aspect, same thing. I found with the 2-foot, I've just got all this noise, and what I'm looking for is a very clear delineation, if I can, of where the aspects change and how they change, because that's how I might break up areas based on which direction the land is facing, one for farming and one just for sun exposure. So I found, both the 10-foot and the 20-foot kind of give me the same thing. So either one could work. I don't gain much, I have a little bit of noise in the 10-foot, nothing substantial. Contours. So when I create the contours using the 2-foot DM, as you can see, I start to get these a lot of jaggedness. And in fact, if I zoom in on this area, not only are these contours super jagged, but you'll see, if you really squint, you'll see tiny little micro contours that are created as well. So there's a lot of noise. And I know if I have a lot of noise now, I'm going to have to clean that up later. So it's a lot of work. So is that high resolution really worth it? No, not in my world. So instead, if I use the 20-foot DM, you can see the contours are pretty much the same direction, but they're just nice and smooth. And they're so true. I mean, you can see this drainage right here is right down in the bottom of those contours. This road here, I know there's a drainage right next to it, and you can see right next to it are the bottoms of those contours. I mean, fantastic data. It really, really is. So what did we use before LiDAR? Well, we, for many, many years, have been using the USGS national elevation data, which typically 30-foot resolution DM. And for the most part, this data was very representative of the topography that we found on the property. Okay, in areas where it said it would be steep, yeah, it's steep. But was it precise on exactly how steep? Things like that. Probably not, compared to once I started using the LiDAR data, because this is far more accurate, and it actually highlights to us the inaccuracies of the NED data when we compare it. So let's do a quick comparison just on contours created from the NED data. So you can see for the same area we've been looking at, and from the USGS LiDAR data, where you can see some differences. But I want to highlight an area where it's pretty significant, the difference. As you can see here, it makes it look like we've got a big knob right there in the topography. That's significant when we're looking at perhaps planting a vineyard. But in truth, it's actually pretty smooth slope, according to the LiDAR data. So what caused this? It could be, the NED data is pretty old data. It could be that the land used to be like that, and over farming and maybe some grading, that knob has disappeared. Or it could just be the inaccuracies back then of the technology. Whatever it is, I know that when I went out there, this is what I actually saw. And this I'd be scratching my head a little bit on it. So the resulting slopes, they look pretty much the same, to a casual observer. But once you start digging into the data a little bit more, and especially that same area I highlighted, right here we had slopes more than 30%. The LiDAR says that's not there. It's either it's not there anymore, or it's maybe there was vegetation causing inaccuracies. I don't know. But what I do know is that's pretty significant difference. We can see little differences, say out here as well. This area that says is steep isn't that steep. So we can plant up a little bit higher on that particular one. So things like that. So there are limits to the LiDAR data. It's not, it's not everything yet. I was hoping I could take that LiDAR data and do some amazing detailed 3D visualizations. We do a lot of those for marketing vineyards. But as you can see, it kind of failed on me on the building. I was hoping it would do something kind of cool. But and it could be that I need to do some reprocessing of it. I don't know yet. I just haven't even had time to look at that. But it has some limits. So what have we learned? First thing is networking with other GIS professionals is so important. And we as a community, with our user group meetings and things like that, we have a tendency to share, which is great to help elevate the GIS community locally here. Because every time I go to a users meeting or look at some of the presentations from GISDay, stuff like that, I always reveal a treasure or two that I can take back with me. So NED was representative of the NED data was representative of the topography I found out on each property, but LiDAR is true to the topography. So it takes out any doubts that you might have at any time. So how accurate is the USGS LiDAR data? I don't know. I don't have exact specifications, but what I do know is it's a pretty impressive tool for planning and development. This is not engineering, so we're not to that level where we need that. This is purely for planning agricultural usage. And it really has changed significantly how accurate our data is and how accurate our decision-making are. So I'd like to thank everyone on the committee for the GISDay who's putting all this together. Thank those of you that made it through this presentation with me. My email is here if you have any questions or if there's anything you'd like to correct me on. I'm always learning more, so I appreciate any type of feedback. Thank you, and have a great GISDay. Goodbye.